Step outside tonight, find the Andromeda Galaxy, that faint smudge hanging above the constellation Andromeda, and understand that what you're looking at is 1 trillion stars moving toward you right now at 110 kilometers per second. For 13 years, every textbook said the same thing. Andromeda hits us in roughly 4 billion years. Done deal, settled science. Then in June 2025, a single paper quietly changed that certainty to a coin flip without touching a single number about Andromeda's speed. Tonight we walk the full collision, star by star, billion year by billion year. And then we get to the twist that changes everything. If you're new here, subscribe and get comfortable. You're going to want to stay for this one. Part 1. The Night That May Not Exist. There is a smudge in the sky tonight that is going to change everything you think you know about the future. You can see it with the naked eye if you know where to look. Step outside on a clear night, find the constellation Andromeda, and look for a faint, elongated blur of light sitting just above the main line of stars. It does not look like much. It looks like someone breathed on the glass of the universe and forgot to wipe it clean. Most people who have ever looked up at it assumed it was a cloud, a smear of gas, something local and unremarkable. But that smudge contains approximately 1 trillion stars. It is 2.5 million light-years away from where you are sitting right now, and it is moving toward you at 110 kilometers per second. Let that velocity settle for a moment before we move on, because it is easy to hear a number like that and let it wash over you without really feeling it. 110 kilometers per second means that in the time it takes you to read this sentence, Andromeda has closed roughly 1,000 kilometers of the gap between itself and you. It has been doing this for billions of years. It will keep doing this for billions more. And for the better part of a century, the scientific consensus was that this approach had only one possible ending, a catastrophic, beautiful, galaxy-scale collision that would reshape both the Milky Way and Andromeda into something entirely new. That event even has a name. Astronomers call it Milkomeda. It is the merged remnant that would be left behind after 2 of the largest galaxies in the local group have consumed each other, swirled together over hundreds of millions of years, and settled into a new equilibrium. Textbooks described it, documentaries visualized it, lectures treated it as settled fact, as one of the few things about the deep future that astronomers had genuinely, rigorously worked out. The collision was expected to begin in approximately 3.9 billion years, with a final full merger taking another billion or 2 beyond that. It was, in the language of popular science, a done deal. And then June of 2025 happened. A paper appeared in the journal Nature Astronomy, authored by Till Sawala and colleagues, and it did something remarkable. It did not discover new motion in Andromeda. It did not revise the speed at which Andromeda is approaching. It did not find a new galaxy in the way, or detect a repulsive force that nobody had considered. What it did was far more unsettling than any of those things. It revised our understanding of the Milky Way's own motion, and in doing so, it downgraded the most confidently stated prediction in popular astronomy from near certainty to something closer to a coin flip. The paper estimated roughly a 2% chance of collision within 5 billion years and roughly 50% within 10 billion years. Stop and sit with that for a moment. Nothing about Andromeda changed. The smudge in the sky is moving at exactly the speed it was always moving at. The problem was not with Andromeda. The problem was that we had been watching Andromeda approach from a reference frame we assumed was stationary, and our reference frame is not stationary. We had been standing on a moving platform, measuring the motion of an incoming train, without accounting for the fact that our own platform was drifting sideways. That is the central paradox at the core of this entire story, and we are going to spend the next few hours walking through every dimension of it. Because here is the thing. Everything we know about what will happen the night Andromeda collides with the Milky Way is still accurate. The physics is correct. The simulations are extraordinary. The timeline, the starburst, the supermassive black holes spiraling together, the birth of a new elliptical galaxy, all of it holds together beautifully. We can walk through that night in extraordinary detail. We just cannot tell you with confidence whether that night is ever actually going to arrive. That is not a small distinction. To understand why this matters so much, you have to understand how thoroughly this collision had been embedded in our model of the future. Ask any astronomer, any physics teacher, any science communicator what the long-range forecast for the Milky Way is, and for the past decade and more, the answer was essentially the same. Andromeda is coming. In 4 billion years, give or take, the two galaxies will begin their fatal embrace. The night sky, as seen from Earth, assuming anyone or anything is still around to observe, it will gradually fill with the approaching disk of our neighbor until it dominates the entire sky. Then the tidal forces will begin to distort our own galaxy from within, and the slow, grinding, glorious catastrophe of a galactic merger will unfold over timescales that make human civilization look like the blink of an eye. The confidence in that prediction was extraordinary. In 2012, a team using the Hubble Space Telescope managed to measure not just how fast Andromeda was approaching, but how much sideways motion it had, a measurement that had seemed almost impossibly difficult to make given the enormous distances involved. The results suggested that Andromeda's sideways velocity was almost negligibly small, something in the range of 17 kilometers per second. That number was critical. It meant that Andromeda was not going to slide past us at a glancing angle. It was coming in nearly head-on. Direct collision. Game over for both galaxies as independent structures. And then the 2025 paper arrived, and it turned out that the critical missing variable was not something exotic or invisible or located in some far corner of the universe. The missing variable was an object we have known about for centuries, an object visible to the naked eye from the southern hemisphere, something so familiar it barely registers as a potential source of cosmological uncertainty: the Large Magellanic Cloud. We will get to why the Large Magellanic Cloud matters in ways that almost nobody expected. We will get to the barycenter of the local group and what it means to measure motion from within a moving system. But first, let us go back to the beginning, because the story of how we even came to believe in this collision is itself a story about what happens when incomplete measurements create the feeling of certainty before the whole picture is in place. What you need to understand before we go anywhere else is that the smudge in the sky is real. 2.5 million light-years of real, 1 trillion stars of real, 110 kilometers per second of real. The question is simply this: where exactly is it going, and where exactly are we going, and whether those two trajectories are ever actually going to intersect? That question, it turns out, is harder to answer than almost anyone suspected. Part 2. The first person who saw it coming. The story of how we first understood that Andromeda was approaching begins in a modest observatory in Flagstaff, Arizona, in the year 1912, with a quietly methodical astronomer named Vesto Slipher doing something that nobody had thought to do before. Slipher worked at the Lowell Observatory, which had been built primarily to search for evidence of life on Mars, a goal that had already started looking dubious by the time Slipher arrived. He had been assigned the less glamorous task of studying what were then called spiral nebulae, faint, fuzzy objects scattered across the sky that astronomers at the time assumed were clouds of gas and dust located somewhere within our own galaxy. Nobody was particularly excited about spiral nebulae. They were not the flashy targets that attracted attention. But Slipher was a precise, patient observer, and he had access to a spectrograph, an instrument that splits light into its component wavelengths, the way a prism spreads sunlight into a rainbow, and he decided to turn it toward the most prominent of these faint smudges, the one in Andromeda. What the spectrograph does, when pointed at a distant object, is reveal the chemical fingerprint of the light coming from that object. Certain elements absorb light at very specific wavelengths, leaving dark gaps called absorption lines in the spread of color. Hydrogen does it, helium does it, calcium, sodium, iron, all of them leave identifiable marks in the spectrum. And here is the critical part. If the object is moving toward you, those absorption lines appear shifted toward the blue end of the spectrum compared to where they should be. If the object is moving away from you, they shift toward the red. The amount of shift tells you the speed. This is the Doppler effect applied to light, and it works with extraordinary precision. Slipher pointed his spectrograph at the Andromeda Nebula, collected his data over several painstaking nights. The exposures required were long because the object was faint, and then measured the position of the absorption lines in the resulting spectrum. What he found was a blue shift so large that he reportedly checked his calculations multiple times before accepting them. Andromeda was approaching at a velocity that was, at the time, simply unprecedented. Nothing in the sky had ever been measured moving that fast toward us. The number he arrived at was around 300 kilometers per second, which is slightly higher than the refined modern figure of 110, partly because the full picture of galactic relative motions was not yet available to him. But the direction was unmistakable. Andromeda was not drifting. Andromeda was incoming. Here is the thing, though, that makes Slipher's discovery both brilliant and incomplete in a way that connects directly to our central question about whether this collision is actually going to happen. Slipher measured the radial velocity, meaning the component of motion directly toward us or away from us along our line of sight. What a blue shift tells you is how fast something is closing the gap between you and it in a straight line. What it cannot tell you, on its own, is whether the object is heading directly at you or sweeping past at an angle. Imagine standing on a street corner watching a car approach. You can hear the engine pitch change as it gets closer. That is your Doppler shift. But just from the pitch, you cannot tell whether the car is aimed straight at you or heading for the street across the intersection. To know whether you are about to be hit, you also need to know the sideways motion. Slipher did not have the tools to measure that. Nobody in 1912 did. The sideways motion of an object as far away as Andromeda, what astronomers call the transverse or tangential velocity, requires tracking the object's position against background reference points with extraordinary precision over long periods of time. In 1912, that was simply beyond reach. So Slipher had half the equation, and it was the dramatic half, the part that said something is coming fast. The other half, the part that would eventually tell you whether it was headed straight for you or skirting past, would have to wait. There was another layer of incompleteness in Slipher's picture that matters even more directly to our story. When he made his measurement, the scientific consensus held that the Milky Way was essentially the entire universe. The spiral nebulae were understood to be objects within our own galaxy, local gas clouds, modest in scale. Andromeda was not yet understood to be a separate galaxy. It was a fuzzy object within what was presumed to be a single, unified Milky Way. That meant Slipher's measurement, extraordinary as it was interpreted through a completely wrong model of what Andromeda actually was. It was not until 1923 that Edwin Hubble, working at the Mount Wilson Observatory in California, resolved that ambiguity in a way that restructured our entire understanding of the cosmos. Hubble was studying a class of stars called Cepheid, variable stars, stars that pulsate in brightness with a regular period, a period that is directly related to their intrinsic luminosity. If you know how bright a star actually is, and you measure how bright it appears from Earth, you can calculate the distance. Cepheids are, in effect, cosmic measuring rods. Hubble found Cepheid variable stars in Andromeda. He measured their period, He calculated their distance, and the number he got was so large that it could not possibly place Andromeda inside the Milky Way. Andromeda was not a local gas cloud. It was an entirely separate galaxy, located at a distance that made the Milky Way itself look modest in comparison, an island universe. To use the terminology of the time, floating in a void that was far larger than anyone had seriously imagined. Go back now and reread Slipher's measurement with that new understanding, because this is where the story of the Andromeda collision really begins. Slipher had not measured a gas cloud approaching at extraordinary speed. He had measured an entire galaxy, a structure containing hundreds of billions of stars, as massive or more massive than our own, approaching at extraordinary speed. The scale of what was coming had just jumped by many orders of magnitude. This is the foundation on which a century of thinking about the collision was built. Slipher provided the velocity, Hubble provided the scale. Together, their measurements created what felt, over the following decades, like the skeleton of a prediction. Something enormous is coming, and it is coming fast. But notice what was still missing: the sideways motion, the precise mass of both galaxies, the influence of everything else in the neighborhood, the position of the observer within a moving system. All of those gaps would eventually matter in ways that nobody fully appreciated until 2025. And the way they mattered is precisely why the most detailed prediction in popular astronomy turned out to rest on a foundation with a crack running through it. The crack was not visible for a long time because the part of the story that was known was so dramatic and so vivid that it drew all the attention. An entire galaxy is heading toward us at over 100 kilometers per second. That is a remarkable thing to know. The question of whether you fully understand the geometry of that approach is easy to overlook when you are still marveling at the speed. Part 3. The moment we thought we solved it. For decades after Hubble established Andromeda as a separate galaxy, the Andromeda collision was more of a qualitative prediction than a quantitative one. Astronomers knew the approach velocity. They could do rough estimates of timing based on the distance and the closing speed, but there were critical unknowns that made precise prediction difficult. Chief among them was the tangential velocity problem, the question of how much sideways motion Andromeda had relative to the Milky Way. This matters enormously, and an analogy makes it immediately clear. Imagine you are standing in an open field, and you know that a large boulder is rolling at 40 kilometers per hour somewhere in the general direction of the field. If it is aimed directly at you, you have a problem. If it has even a small lateral component to its motion, the question of whether it actually hits you becomes much more sensitive to the exact angle than to the speed. A boulder aimed 5 degrees off-center might miss you completely. That is the tangential velocity problem for Andromeda. A relatively small sideways motion could mean the difference between a direct collision and a near miss that leaves both galaxies largely intact. Measuring the tangential velocity of Andromeda is extraordinarily difficult, and the reason is one of those facts about the universe that stops you in your tracks when you really think about it. Even though Andromeda is approaching at over 100 kilometers per second, it is so far away, 2.5 million light-years, that the apparent change in its position on the sky over any human observable timescale is essentially zero. You cannot simply photograph it tonight and again next year and measure how far it has moved across the background of more distant galaxies, because the motion is far too small for that. You need either an enormously long baseline of observations or an instrument of extraordinary precision. The Hubble Space Telescope, launched in 1990, eventually provided that instrument, and in 2012, a team led by astronomer Roland van der Merel published what was immediately recognized as a landmark result. Using Hubble observations taken years apart, they had tracked the positions of individual stars within Andromeda against the background of distant galaxies, objects so remote that they could be treated as essentially fixed points on the sky. By measuring the tiny, tiny shift in the positions of Andromeda's stars relative to those background references, they were able to extract the tangential velocity component. The number they got was approximately 17 kilometers per second. To put that in context, the approach velocity along our line of sight was about 109 kilometers per second at the time of that measurement. The sideways drift was 17. Run that geometry, and what you find is that Andromeda was moving in a direction that would bring it extremely close to a head-on collision with the Milky Way. Not a glancing blow, not a near miss. A direct, full-on collision between two of the largest galaxies in our cosmic neighborhood. The simulations that followed this measurement were spectacular. Cox and Loeb had already done important earlier work in 2008, and the 2012 result refined and validated the broad picture they had painted. What those simulations showed was a canonical timeline, a first close pass between the two galaxies at around 3.9 billion years from now, followed by a chaotic interaction lasting hundreds of millions of years, and then a final merger somewhere around 5.5 to 6 billion years from now. The merged remnant would be an elliptical galaxy, no more spiral arms, no more orderly disk rotation shaped like a smooth, glowing football of stars orbiting in complex, randomized paths. There was a scientific dissident voice worth mentioning, even during this period of growing consensus. In 2016, a researcher named François Salomon published an independent analysis that arrived at a very different tangential velocity for Andromeda, something in the range of 164 kilometers per second, not 17. His method was different, his assumptions were different, and his conclusion was that the collision might not be nearly as clean and direct as the dominant model assumed. But his result was in tension with the Hubble measurement, which was seen as more technically rigorous, and for the most part the field moved on without taking the discrepancy too seriously. That was not necessarily an unreasonable decision at the time. Science routinely encounters conflicting measurements, and the weight of evidence often justifiably favors one result over another. But in retrospect, Salomon's number contained a signal that was pointing at something real, a warning that the geometry of this system might be more uncertain than the dominant model assumed. Underneath all of this, there was an assumption so deeply embedded in the analysis that almost nobody thought to question it explicitly. The Milky Way was being treated as a stationary reference point. The whole problem was set up as, Andromeda is here, it is moving at such and such velocity. The Milky Way is here, it is not going anywhere important. When do they meet? That framing is natural, almost compulsory, when you are doing the analysis from inside the Milky Way. Of course you use your own galaxy as the reference frame. Where else would you stand? But here is the problem, and it is the same problem that unraveled everything in 2025. The Milky Way is not stationary. It is moving through the local group under the gravitational influence of everything around it, including Andromeda, including the Triangulum Galaxy, and including an object that nobody had properly accounted for in these collision calculations, the Large Magellanic Cloud. The Large Magellanic Cloud is a satellite galaxy of the Milky Way. From the southern hemisphere, it is easily visible to the naked eye. It looks like a detached piece of the Milky Way hanging in the sky, which, in a sense, is exactly what it is. It contains tens of billions of stars, and it orbits our galaxy at a distance of around 160,000 light-years. For a long time, it was modelled as a relatively minor satellite, something in the range of 10 billion solar masses, a small fraction of the Milky Way's total mass of roughly 1 trillion solar masses. At that size, it would tug on the Milky Way slightly, but not in any way that would significantly affect the Andromeda calculation. More recent estimates, however, have pushed the mass of the Large Magellanic Cloud substantially higher, potentially up to 250 billion solar masses, which is around a quarter of the Milky Way's mass. That is not a minor satellite. That is a major gravitational player, and it is not just sitting there quietly. It is actively pulling the Milky Way in a direction that the classic collision models never accounted for. And when you add a gravitational tug of that magnitude to the calculation, the Milky Way's trajectory through the local group looks meaningfully different than it did in the simpler model where the Milky Way was essentially standing still. That single correction is what changed a near certainty into a coin flip, and we will explore exactly how in the final act of this story. But first, let us assume the classic collision happens because the physics of what it would look like is extraordinary, and understanding it is not wasted, even if the event itself turns out to be uncertain. If Andromeda is coming, this is what the night looks like. Part 4. When the sky breaks open. Imagine standing outside on a clear night 3.9 billion years from now. The first thing you would notice, assuming there was anyone left to notice anything, which we will come back to, is that the sky is wrong. Not catastrophically wrong, not exploding in all directions wrong. The wrongness would be subtle at first, and it would have been building so slowly over so many millions of years that no individual observer across all of that time would have noticed the change in a single lifetime. But if you could somehow compare a photograph of the sky from tonight with a photograph taken 3.9 billion years from now, the difference would be staggering. The smudge in Andromeda that you can barely make out with the naked eye tonight would, over that timescale, have grown from a faint blur into one of the most dominant objects in the entire sky. The approach is slow by any human standard. 110 kilometers per second sounds fast, but across 2.5 million light years, it takes an extraordinary amount of time to close the distance meaningfully. At current speeds, Andromeda closes roughly 3.4 billion kilometers of distance every year. That sounds impressive until you realize that the full gap is approximately 24 quintillion kilometers, so the annual progress is barely a rounding error. This is not a fast collision. It is a geological process playing out at galactic scale. But time is patient, and over billions of years, the math compounds. At around 1 billion years from now, Andromeda would begin to look noticeably larger to any hypothetical observer than it does tonight, not dramatically, but measurably. The way a thunderstorm that is 3 counties away starts to develop visible structure when it gets to 1 county away. By 2 billion years from now, the disk of Andromeda would be clearly visible as a structured object. Not just a smudge, you could see the central bulge, trace the spiral arms, watch the arrangement of its stars shift over timescales that still dwarf human civilization, but that are compressed into something appreciable when you are watching billions of years pass. By 3 billion years from now, Andromeda would span a significant fraction of the sky. By 3.5 billion years out, it would be larger in apparent size than the full moon is tonight. By the time first passage is imminent, Andromeda would be one of the most visually spectacular objects that any observer in the galaxy had ever seen. A full, structured, companion galaxy spanning much of the visible night sky, close enough that the tidal forces between the two systems would already be leaving their mark on the distribution of stars in both galaxies. Those tidal forces are where the physics starts to get genuinely strange, and it is worth understanding what they actually are before we watch them tear both galaxies apart in slow motion. Tidal force arise from gravitational gradients. The basic concept is this: gravity falls off with distance, following an inverse square law, which means that the side of an object closer to a gravitational source feels a stronger pull than the side farther away. For small objects, this difference is negligible, but for something the size of a galaxy, stretched across tens of thousands of light years, the difference in gravitational pull between the near side and the far side of the structure when another galaxy is approaching becomes enormous. What this means practically is that stars on the near side of the Milky Way get pulled harder toward Andromeda than stars on the far side. And stars on the far side, experiencing relatively less pull, effectively get left behind relative to the center of mass. The result is that the galaxy stretches, drawing out long streamers of stars called tidal tails, structures that can extend for hundreds of thousands of light years in both directions, like a galaxy being pulled into a cosmic taffy machine. We can observe this process in other galaxy pairs throughout the universe. There are systems, like the Andromeda galaxies, named for the two long tidal tails extending from them, like insect antennae, and the mice galaxies, and dozens of others at various stages of the merging process. They tell us what the Milky Way and Andromeda would look like from the outside, during this phase chaotic, distorted structures, trailing brilliant threads of displaced stars behind them. From the inside, though, the experience would be very different from what you might expect, and this is one of the most important points about this entire event. Despite everything being described here, the night sky would not look like an explosion. The stars would not be crashing into each other. The solar system would not be in immediate physical danger from the collision itself. And the reason comes down to a fact about stellar density that is profoundly counterintuitive until you actually work through the numbers. Stars are, relative to the distances between them, almost unimaginably small. The nearest star to the Sun, Proxima Centauri, is approximately 4.2 light-years away. The Sun itself is about 1.4 million kilometers in diameter. The average distance between stars in the Milky Way is measured in light-years. Now, a light-year is approximately 9.5 trillion kilometers. So the gap between any two neighboring stars is roughly 100 million times larger than the stars themselves. When two galaxies pass through each other, it is not like two clouds of sand colliding where individual grains smash together. It is more like two swarms of fireflies passing through each other in the dark. The fireflies almost never hit anything. What does get disrupted is the larger scale orbital structure, the paths that stars trace around the galactic center over millions of years, but the stars themselves sail through, perturbed but not destroyed. What this means for the solar system is not imminent physical collision with another star. What it means is gravitational disruption of the solar system's orbital position within the galaxy. The Sun's path around the galactic center, which currently takes it on a roughly circular orbit, completing one revolution every 225 million years or so, could be significantly altered by the gravitational chaos of the merger. We will look at the specific statistical outcomes for the solar system in a later section, but the short version is, the danger is displacement, not destruction. The solar system could end up flung into a very different part of the merged galaxy, or even ejected from it entirely, without a single star directly colliding with another. Meanwhile, as the stars sail through each other largely unharmed, something else is happening in the spaces between them, something that does involve direct physical collision, and something that is going to produce one of the most extraordinary light shows in the history of either galaxy. Part 5. The brightest destruction in galactic history. Between the stars of the Milky Way, filling the spaces that look empty from a distance, there is an enormous amount of material that is most definitely not going to pass through the merger unharmed. This is the interstellar medium clouds of hydrogen and helium gas, dust particles, molecular clouds, where temperatures drop low enough for simple chemistry to occur. In some regions, these clouds are dense enough that new stars are already forming within them, lit from inside by the gravitational compression of collapsing gas. In others, they are so thin and cold that they float for hundreds of millions of years without doing much of anything. When Andromeda passes through the Milky Way, the gas does not simply sail through unaffected the way the stars do. Gas clouds collide with gas clouds. And unlike stellar encounters, gas collisions are direct, physical, violent events. Two clouds of gas running into each other at the velocities involved in a galaxy merger do not gently mix. They slam together, compress, heat up, and radiate enormous amounts of energy. The technical term for what happens next is a shock, and shocks are one of the most productive phenomena in astrophysics because they do something extraordinary. They compress the gas to densities high enough to trigger gravitational collapse, and gravitational collapse is how stars are born. This is the starburst phase of the merger, and it is genuinely one of the most spectacular processes in the observable universe. Under normal conditions, star formation in a galaxy like the Milky Way proceeds at a leisurely rate, perhaps a handful of new stars per year, on average, scattered across tens of thousands of light years. During a major merger-driven starburst, that rate can jump by a factor of 10, 50, or even 100. Hundreds of millions of new stars can form in a relatively brief cosmological window of a few 100 million years, concentrated in certain regions of the merging system where the gas compression is most intense. And here is where it gets even more interesting, because not all of those new stars are alike. The most massive stars, those containing 10, 20, 50 times the mass of our Sun, form quickly, burn furiously, and die fast. A star like our Sun will live for roughly 10 billion years. A star with 30 times the Sun's mass might live for only a few million years before exhausting its nuclear fuel and exploding as a supernova. During a starburst, the sheer rate of massive star formation means that supernova explosions are going off continuously, scattered across the merging system like fireworks that never stop. Each supernova releases approximately 10 to the power of 44 joules of energy. More energy than the Sun will radiate in its entire 10 billion year lifetime in a matter of seconds. The cumulative effect of millions of supernovae firing in rapid succession across a galaxy is staggering. The exploding stars blast processed heavy elements, carbon, oxygen, silicon, iron, into the interstellar medium, enriching it with the chemical building blocks of planets and potentially life. They drive enormous shockwaves through the surrounding gas, triggering yet more star formation in a cascade that can sustain itself for hundreds of millions of years. They produce radiation across every wavelength, from radio waves to gamma rays, flooding the entire merging system with energy at a rate that would make the present-day Milky Way look serene by comparison. We do not have to speculate about this process in the abstract, because we can observe it happening right now in other galaxies throughout the universe. Systems known as starburst galaxies, galaxies currently undergoing extremely rapid star formation, often triggered by a nearby gravitational interaction, are luminous in ways that dwarf ordinary galaxies. Some of them radiate more energy in the infrared wavelengths alone than the entire Milky Way produces across all wavelengths combined. They are cosmic events in progress, captured by our telescopes at various stages of their development, and they give us a direct observational template for what Milkomeda might look like during its most active phase. There is another component to the energetic fireworks of the merger that we cannot overlook, and it operates on an even grander scale than the starburst. At the center of both the Milky Way and Andromeda, there are supermassive black holes. Ours is called Sagittarius A star, and it has a mass of approximately 4 million solar masses. Andromeda's central black hole is substantially larger. Estimates put it in the range of 100 million solar masses, roughly 25 times more massive than ours. Under normal conditions, both of these objects are relatively quiescent. There is not a large supply of gas falling into them at any given moment, so they are not producing much radiation. They just sit there, warping space-time in their immediate vicinity, invisible except for their effects on surrounding stars. During the merger, that changes. The gravitational chaos and gas cloud collisions that drive the starburst also funnel enormous quantities of gas toward the central regions of both galaxies. When gas falls into a supermassive black hole, it does not go quietly. It forms a blazingly hot accretion disk around the black hole, a swirling vortex of matter heated to temperatures of millions of degrees, and in some cases it drives jets of relativistic particles blasting outward from the poles of the black hole at close to the speed of light. Objects powered by this process are called active galactic nuclei, and at their most extreme, they become quasars, among the most luminous objects in the entire observable universe, outshining entire galaxies by factors of hundreds or thousands. Whether Milky actually produces a full quasar phase depends on how much gas reaches the central black holes during the merger, and on the specifics of how and when the two black holes interact with each other. But the possibility is real, and some simulations suggest that the merger could temporarily produce an active galactic nucleus luminous enough to be visible across the local group, perhaps even across cosmological distances. For a period that might last tens or hundreds of millions of years, Milky could become one of the most energetically active galaxies in its neighborhood of the universe. All of this light, all of this energy, all of this creative destruction happening simultaneously across a system containing 2 trillion stars. And yet the most extreme physical event of the entire merger, the one involving the most energy concentrated in the smallest volume in the shortest time, would be producing no visible light at all. Part 6. The invisible catastrophe beneath it all. While the starburst is lighting up the merging galaxy across every wavelength of the electromagnetic spectrum, and while accretion onto the supermassive black holes is potentially powering a quasar phase that outshines entire galaxy clusters, something else is happening in the deepest interior of the system that no human eye or any eye operating in any wavelength of light would ever be able to observe. The 2 supermassive black holes at the centers of the Milky Way and Andromeda are sinking toward each other. The process is called dynamical friction, and it works through the gravitational interaction of a massive object with the surrounding sea of stars. As each black hole moves through the core of the merged system, it exerts a tiny gravitational tug on every star it passes near. Those stars absorb a tiny bit of momentum from the black hole, and by Newton's third law, the black hole loses a tiny bit of momentum to each star. Over millions of years, this continuous transfer of momentum acts like a brake. It causes the black holes to spiral inward toward the center of the merged system, losing energy and angular momentum to the surrounding stellar population. Eventually, and the timescale is uncertain, potentially hundreds of millions of years after the final merger, the 2 black holes come close enough to each other that they form a gravitationally bound binary system. At this point, they are no longer being braked primarily by dynamical friction with the stellar background. They are spiraling together under the emission of gravitational waves. Gravitational waves are ripples in space-time itself, distortions in the fabric of space and time that propagate outward at the speed of light, carrying energy away from the system that produced them. They were predicted by Einstein's general theory of relativity in 1916, and their existence was confirmed a century later by the LIGO detectors in 2015, when they detected the merger of 2 stellar mass black holes. The merger of 2 supermassive black holes at the scale of Sagittarius A star and Andromeda's central black hole would produce gravitational waves of a frequency and amplitude so extreme that they would be detectable across enormous distances, potentially detectable by the LISA observatory, the Laser Interferometer Space Antenna, if it is operational at the right time. The energy released in the final seconds of that merger would be almost beyond description. The 2 black holes, each containing tens or hundreds of millions of times the mass of the Sun, spiraling together and finally merging into a single object, would radiate a fraction of their combined mass energy directly into gravitational waves, in a burst that would briefly rival the combined luminosity of every star in the observable universe, expressed entirely in a medium that carries no light, makes no sound, and is detectable only by measuring the compression and stretching of space-time itself at a level smaller than a proton. This is the invisible heart of the Andromeda collision, the most energetic event in the entire process, completely hidden from any observer relying on conventional astronomy. And here is the connection back to the central question we began with. Even this most precisely modeled and most dramatic component of the merger depends entirely on one thing. The two galaxies have to actually merge. They have to come close enough, slow down enough, and interact deeply enough that their central black holes end up in the same merged system. If the 2025 paper is correct, if the collision is genuinely uncertain, if there is a real possibility of a flyby or a permanent separation, then the black hole merger may never happen. The gravitational wave burst that would ripple across the local group may never occur. Everything we have just described, from the tidal tails to the starburst to the quasar phase to the black hole in spiral, rests on a premise that has just become probabilistic rather than certain. And that changes the nature of everything that follows. Part 7. The Fate of the Solar System. Within the broad drama of two colliding galaxies, there is a much smaller question that nevertheless tends to be the one people ask first, because it is the most personal. What happens to us? The answer depends, of course, on whether the collision happens at all, and even if it does, the solar system's specific fate within the larger chaos is statistical rather than predetermined. Simulations of the merger run thousands of test particles representing objects like the solar system and track where they end up after the merger has played out. The results are probabilistic, in the same way that a pinball machine is probabilistic. You can describe the general distribution of outcomes, but you cannot predict the exact path of any individual ball. The most common outcome for a solar system-like object in these simulations is outward migration. Something on the order of 50% of the objects in the inner disk of the current Milky Way end up in a larger orbit within the merged galaxy, displaced from their current neighborhood, shuffled outward, but still part of the gravitational family. This sounds alarming, but is, in practical terms, not immediately catastrophic for the Sun and its planets. The Sun would still be the Sunday, its nuclear fusion would continue on its own schedule, the planets would remain in orbit around it. The sky, if there were anyone around to observe it, would look very different, because you would be looking out from a different position within a differently structured galaxy. But the local environment would not be dramatically altered by the migration itself. Approximately 12% of solar system analogues in these simulations get ejected entirely from the merged galaxy. This is the scenario where the gravitational scattering during the merger is severe enough to give the solar system a velocity kick that exceeds the escape velocity of Milky. If this happened, the Sun would depart on a trajectory that would eventually carry it into intergalactic space, the vast, essentially empty void that lies between galaxies. Over hundreds of millions of years, the Sun would travel through a region of the universe that contains almost nothing. No star clusters, no nebulae worth mentioning, no galactic structure at all. The night sky from an ejected solar system would eventually become one of the most profoundly lonely views in the universe. A few dozen distant galaxy clusters, visible as smudges, no nearby stars, the Milky Way and Andromeda receding behind you as you drift through the dark. A small fraction of the simulations, something like 2 to 3%, result in the solar system actually being captured by Andromeda's remnant rather than staying with the Milky Ways. So there is a non-trivial statistical chance that, if the collision happens, the solar system ends up as a citizen of what used to be the Andromeda Galaxy rather than the Milky Way. What none of these scenarios involves, and this bears repeating because it is the most common misconception about the collision, is a direct physical encounter between the Sun and another star. The stellar densities involved in even the most chaotic phase of the merger are simply too low for that to be a meaningful probability. Stars passing close enough to perturb planetary orbits within the solar system is a real concern during the densest phase of the interaction. But direct collision between two stars remains astronomically improbable even in the middle of a galaxy merger. The galaxy is just too much empty space for stars to find each other. The solar system's fate, then, is one of displacement and uncertainty, rather than destruction, which is, in its own way, a kind of cosmic answer to the most personal question the collision raises. We would not be annihilated. We would be scattered, perhaps exiled, perhaps captured by a different gravitational family. But the sun would keep burning, and the planets would keep circling, carried along by the gravitational chaos without being torn apart by it. Whether any of this matters for life on Earth, though, depends on a timeline mismatch that makes the entire question somewhat academic. And it is a mismatch that almost nobody mentions when they discuss the Andromeda collision. Part 8. The part nobody tells you. There is something quietly strange about the way we discuss the Andromeda collision in popular science, and it has to do with a different, closer catastrophe that will unfold on a much shorter timescale than the one we have been discussing. It is a catastrophe that almost never gets mentioned in the same breath as the galaxy merger, even though it is the more personally relevant of the two events by an enormous margin. And once you understand it, the emotional register of the entire Andromeda story shifts in a way that is difficult to unfeel. The sun is not a stable object. It is a star, which means it is powered by nuclear fusion, specifically by the conversion of hydrogen into helium in its core. As hydrogen gets used up and helium accumulates, the composition and structure of the sun's core gradually changes over billions of years. The core contracts slightly under gravity, the fusion rate increases to compensate, and the outer layers of the sun expand in response. The result is that the sun is slowly, steadily, inexorably getting more luminous. Not fast enough to notice in a human lifetime, not fast enough to show up in any instrument we have built in recorded history. But over geological timescales, the kind of timescales that built the Himalayas and carved the Grand Canyon and opened and closed entire ocean basins, the increase is real and it is relentless. Current estimates suggest that the sun's luminosity increases by roughly 10% every billion years. That sounds modest at first. 10% is the kind of number you see on a grocery receipt, not in a cosmological catastrophe. But the implications for Earth's long-term habitability are anything but modest, because the sun's luminosity is the primary dial controlling the temperature of this planet, and that dial is being slowly, permanently turned up. Earth sits in what astronomers call the habitable zone, the range of distances from a star where surface temperatures allow liquid water to exist. Not too hot, not too cold. We are in that zone right now, which is rather obviously why we are here to discuss it. But the habitable zone is not a fixed address in the solar system. It is defined by the sun's luminosity, and as the luminosity increases, the zone migrates outward. Earth's position relative to the inner edge of that zone is not a permanent arrangement. It is a temporary coincidence of distance and stellar output that has lasted for billions of years but will not last forever. The models of Earth's long-term climate suggest that somewhere in the range of 1 billion years from now, roughly a quarter to a third of the time remaining before the Andromeda collision even begins, the sun will be luminous enough to trigger a runaway greenhouse effect on Earth. The mechanism is one of those feedback loops that sounds almost mundane until you trace it all the way to its conclusion. The increased solar energy will warm the surface slightly, causing more water to evaporate from the oceans. Water vapor is a powerful greenhouse gas, more powerful molecule for molecule than carbon dioxide. So more water vapor in the atmosphere means more warming. More warming means more evaporation. More evaporation means more water vapor. More water vapor means more warming. The loop, once triggered past a certain threshold, does not stabilize. It runs away. The end point of that runaway is a planet that no longer has liquid water on its surface at all. The oceans do not simply shrink or retreat to the poles. Over time, they evaporate entirely. The water vapor eventually reaches the upper atmosphere, where ultraviolet radiation from the sun breaks the water molecules apart into hydrogen and oxygen, and the lightweight hydrogen escapes to space, never to return. Earth loses its oceans permanently. What is left behind is a hot, dry, geologically active rock with a thick atmosphere of carbon dioxide and residual gases, something that more closely resembles Venus than the blue world we are sitting on right now. This is not speculative. This is the straightforward physics of a star that is getting brighter applied to a planet at a fixed distance from it. The details of the timeline carry some uncertainty. Some models push the uninhabitable threshold to 1.5 billion years. Others suggest the first serious disruptions to complex life could come within 500 million years, but the direction is not in question. The sun is warming. Earth will eventually follow, and the timescale is billions of years shorter than the Andromeda collision. What this means, when you sit with it for a moment, is that the timeline for complex life on Earth ends roughly 3 billion years before the Andromeda collision even begins. By the time the approaching disk of Andromeda starts to visibly dominate the night sky, by the time the tidal forces begin distorting both galaxies and the first great wave of starburst ignites by that point, the surface of Earth will have been uninhabitable for a span of time longer than the current age of complex animal life on this planet. 3 billion years of an empty stage. 3 billion years of geology and volcanism and ultraviolet bombardment, with no eyes to observe any of it. This is not a small footnote to the collision story. It is not a detail that can be acknowledged briefly and then set aside without consequence. It changes the entire emotional register of the narrative. When we describe what the night sky will look like as Andromeda approaches, when we talk about the galaxy gradually growing from a smudge to a structured disk, to something that spans a significant fraction of the visible sky, we are implicitly imagining an observer, a biological one, something with eyes, or at least with instruments built by something that once had eyes, standing on a habitable world somewhere in the Milky Way and watching the show unfold. That implicit observer is doing a lot of emotional work in the story we tell about the collision. It is the reason the story feels meaningful rather than purely mechanical. It is the reason it feels like something that matters rather than just something that happens. But the honest version of the story acknowledges that no such observer will exist on Earth. The show will go on, but at least from this particular vantage point, the seats will be empty. Unless they are not. And here is where things get genuinely strange to think about. 1 billion years is an almost incomprehensibly long time. The entire history of complex animal life on Earth, from the first multicellular organisms, through the Cambrian explosion, through the age of dinosaurs, through every civilization humanity has ever built, spans roughly 600 million years. 1 billion years is longer than that. It is long enough that any surviving descendant of present-day human civilization would be separated from us by a gulf of time greater than the one that separates us from the first fish to crawl onto land. The technological and biological distance across that span is genuinely beyond imagination. A civilization that has had 1 billion years to develop could, in principle, have spread to dozens or hundreds of other star systems. It could have engineered biospheres on worlds that were previously uninhabitable, built artificial habitats in space, entirely independent of any planetary climate, or diverged into forms of intelligence so different from biological humanity that calling them our descendants would be more metaphorical than literal. The collision that is invisible to any present-day Earth species, happening 4 billion years after the last Earth organism has died, might be watched in extraordinary detail by something that shares a common ancestor with us, but is now entirely unrecognizable as anything we would call biological. Something that chose to keep watching, something curious enough, or long-lived enough, or patient enough to observe a galaxy merger from beginning to end. Or it might be watched by nothing at all. That is also a real possibility, and it is one that tends to produce a particular quality of silence when you actually hold it in your mind without immediately flinching away from it. We assume observers. It is one of the deepest and most persistent assumptions in the way we talk about the future of the universe. We assume that somewhere out there, across the billions of years we are describing, something descended from life will be present to witness the events we are narrating. The starburst, the black hole merger, the long, slow fading of Milky into an aging elliptical of red dwarf stars. We tell these stories as if they are stories for someone, as if the universe is a theatre that has an audience. But the universe has no obligation to provide witnesses. The merger will happen if it happens regardless of whether anything is there to see it. A galaxy collision observed by nobody is still a galaxy collision, playing out across the same timescales, releasing the same energy, producing the same tidal tails and starburst and gravitational waves. The physics does not require an audience. The beauty of it, if beauty is even a meaningful concept without a mind to register it, persists regardless. What we are left with, then, is a prediction of extraordinary detail and precision, describing an event that may not occur on a timescale that extends far beyond any plausible human presence on Earth, witnessed by something we cannot describe, or perhaps by nothing at all. We have worked out the physics of this collision more carefully than we have worked out almost anything else about the long-range future of the cosmos. The simulations are meticulous. The mathematics is correct. The vision of Milky is genuinely one of the most detailed portraits of a future event that science has ever produced. And we will never see it. Sit with that for a moment before we move on, because that particular fact, not the collision itself, but the certainty of our absence from it, might be the most important thing this entire story has to tell us about our place in the universe. Part 9. The Final Sky, Milky Way. Assuming the collision happens, and we are still operating in that assumption, as we approach the moment of final reckoning, the story does not end with the starburst and the black hole merger. Those are the dramatic peak of the event, the explosive crescendo of a process that has been building for billions of years. But what comes after is in many ways more interesting, and in some ways more moving than anything that preceded it. What comes after is the long, slow settling of 2 trillion stars into a new equilibrium, the cooling of the fire, the quieting of the chaos, the gradual emergence of something stable and unfamiliar from the wreckage of 2 of the most beautiful structures in the local group. To understand what Milky eventually becomes, you first have to understand what is being lost. Both the Milky Way and Andromeda are spiral galaxies, and spiral galaxies are, by any reasonable aesthetic measure, among the most visually striking structures in the observable universe. Their defining feature is the disk, a flat, rotating plane of stars, gas, and dust, organized into sweeping arms that wind outward from a bright central bulge like a cosmic pinwheel caught in the act of turning. That structure is not accidental. It is the product of angular momentum, the rotational inertia that a galaxy inherits from the conditions of its formation and preserves over billions of years, the same physical principle that keeps a spinning top upright or a figure skater rotating. Most of the stars in a spiral galaxy follow orderly, roughly circular orbits around the galactic center, all moving in roughly the same direction, all staying within roughly the same plane. It is, by the standards of a system containing hundreds of billions of stars, almost eerily organized. That organization is what galaxy mergers destroy, and the destruction is not quick. It does not happen in a single catastrophic moment. It unfolds over hundreds of millions of years through a process that is less like a collision between 2 rigid objects and more like the interpenetration of 2 enormous, loosely connected clouds of gravitationally interacting points. The tidal disruptions of the initial passes scatter stars out of their orderly orbits. The gravitational chaos of the interaction randomizes orbital inclinations. Stars that once moved in a flat disk begin orbiting at angles to each other, some tilted slightly, some radically, some moving in what amounts to retrograde, relative to the original rotation of their parent galaxy. The organized, roughly coplanar disk dissolves into a three-dimensional swarm, a spheroidal cloud of stars with no preferred plane and no coherent rotational direction. What this process produces, eventually, is an elliptical galaxy, not a spiral with damaged arms, not a disk with a bigger bulge. A fundamentally different kind of structure, smooth, featureless, roughly egg-shaped, without spiral arms or a thin disk or the dramatic band of the Milky Way that you can see stretching across a clear, dark sky. Elliptical galaxies are some of the most common galaxy types in the local universe, particularly in dense environments like galaxy clusters where interactions between galaxies are frequent. We understand now, with reasonable confidence, that most of them did not form this way from the beginning. Most of them were once spirals, once organized and disk-like and visually spectacular, and they lost that structure through exactly the kind of merger we have been describing. They are the remnants of collisions. They are what happens after the fire goes out. Milky would join this population. It would be, in the classification scheme of galaxy morphology, an elliptical, probably a large one, given that it would contain the combined stellar mass of two already massive spiral galaxies, plus whatever stars were born during the starburst phase of the merger. From the outside, observed by some hypothetical civilization in a neighboring galaxy, it would look like a smooth, glowing ellipsoid of stars, with no internal structure worth noting, no arms, no disk, no dramatic concentration of star formation in a thin plane, just a cloud of stars, orbiting in complex, interlocking paths, gradually fading. From the inside, the view would be profoundly different from anything we see today, and it is worth pausing to really imagine what that difference would feel like if you could stand somewhere within Milky and look out. Right now, on a clear, dark night, away from city lights, the Milky Way is one of the most striking features of the night sky. It appears as a luminous band stretching from horizon to horizon, not because there are more stars in that direction, exactly, but because we are embedded in a flat disk and looking along the plane of it. The band is densest and most spectacular toward the galactic center in the direction of Sagittarius, where the core of the Milky Way blazes behind curtains of dust. It thins symmetrically in both directions, eventually fading into the general background of the sky. That band is our disk, seen from the inside. It is the shape of our galaxy expressing itself visually, and it has been a feature of the night sky for every form of life that has ever looked up from the surface of this planet. In an elliptical galaxy, that band is gone. Stars in an elliptical galaxy orbit in all directions, at all inclinations, distributed throughout a three-dimensional volume. There is no preferred plane, there is no disk to look along. An observer inside Milky would see stars distributed more or less uniformly in all directions, not perfectly uniform, because the density would still be higher near the galactic center, but without the dramatic, elongated concentration that defines the Milky Way's appearance from Earth. The sky would be somewhat more uniformly bright across its entire extent. The galactic center would still be apparent as a general brightening in one region of the sky, but it would manifest as a soft glow rather than a defined band, more like a luminous haze, spreading across a large section of the sky than a coherent structure that you could point to and trace from end to end. There would also be fewer stars visible in that sky, in one important sense. Not because Milky would contain fewer stars than the current Milky Way, it would contain far more. But star formation would have declined dramatically in the aftermath of the merger, and the most spectacular stars, the massive, blazingly luminous blue and white giants that currently dot our spiral arms and make the Milky Way so visually rich, would be largely gone. Those stars burn bright and die fast, and the starburst phase of the merger would produce them in enormous quantities, only to consume them within millions of years. By the time Milky has settled into its post-merger equilibrium, the population of massive, short-lived stars would be mostly exhausted. What remains would be older, cooler, redder. This is the critical dynamic shaping Milky's long-term future, the end of star formation. The starburst phase of the merger is, among other things, an act of consumption. The collision drives enormous quantities of gas into regions of high density, triggering rapid and efficient star formation across a system that contains far more raw material than either galaxy currently has available individually. But efficiency has a cost. The starburst burns through the interstellar gas, the raw material from which stars are made, at a rate that vastly exceeds the leisurely pace of star formation in either pre-merger galaxy. The gas supply, while enormous, is not infinite, and once it is gone, it is effectively gone. New stars cannot form without gas to collapse. The starburst is, in a real sense, the galaxy spending its savings all at once. What follows is a process that astronomers sometimes call quenching the gradual extinction of star formation across the merged system. Milky would not immediately stop making stars the moment the last great burst fades. There would be residual pockets of gas, reservoirs in satellite galaxies that eventually get absorbed, material swept in from the outskirts of the system. Star formation would taper rather than stop abruptly. But the trajectory is unambiguous. Over hundreds of millions of years following the merger, the rate of new star formation would fall towards something negligibly small, and the stars that already exist would simply age. Stellar aging is a one-way process, and it is worth understanding what it means for the long-term appearance and character of a galaxy. The most massive stars, those 10, 20, 30 times the mass of the Sun, are already gone within millions of years of their formation, lost to supernovae during the starburst itself. Stars somewhat less massive than that, still luminous and blue-white, live for tens of millions to a few 100 million years before they too exhaust their fuel and either explode or quietly collapse. As time passes after the merger, each successive tier of stellar mass reaches its end, and the surviving population skews progressively toward the lower end of the mass spectrum. The Sun, as a reference point, will live for roughly 10 billion years total. Stars at half the Sun's mass live for perhaps 30 to 40 billion years. Stars at a third of the Sun's mass might live for hundreds of billions of years. And at the extreme low end, red dwarf stars at around 8 to 15% of the Sun's mass, barely hot enough to sustain nuclear fusion at all, lifetimes stretch into the trillions of years. These are not hypothetical objects. Red dwarfs are already the most numerous type of star in both the Milky Way and Andromeda. They just happen to be so intrinsically faint that they contribute very little to the total luminosity of their host galaxies, even though they collectively account for the majority of stellar objects. In the very distant future, tens of billions of years after the merger, in a universe that is already unrecognizably different from the one we inhabit, Milky would be a galaxy dominated entirely by these dim, cool, long-lived embers. The brilliant stars that currently make galaxies luminous across cosmological distances would be gone. The universe itself would be darker, because cosmic expansion would have carried most other galaxies beyond the observable horizon, leaving the local group increasingly isolated in a growing void. Milky would persist, its red dwarf population quietly continuing their trillion-year lives, orbiting in the complex gravitational choreography of the elliptical system, growing slightly redder and slightly dimmer with each passing era. There is something almost peaceful about this image, and it deserves to be held for a moment rather than rushed past. After all of the chaos we have described, the tidal disruptions stretching both galaxies into great arcing streams of displaced stars, the starburst producing hundreds of millions of new stars in a cosmological eye blink, the supernova waves sweeping through the combined system, the supermassive black holes spiraling together and releasing a gravitational wave burst that briefly rivals the luminosity of the observable universe. After all of that violence and energy and transformation, The final state is quiet. 2 trillion stars, each following its own complex orbit through the smooth, three-dimensional volume of the merged system, gradually aging, gradually cooling, gradually fading, not destroyed, not scattered to nothing, just settled. That word settled carries more weight here than it might initially seem, because one of the most important things to understand about the Andromeda collision is what it is not. It is not the destruction of the Milky Way. It is not the annihilation of Andromeda. No stars are erased from existence by the merger in any wholesale sense. The solar system, as we discussed in an earlier section, would survive the collision in most simulations displaced, perhaps significantly, from its current orbital position within the galaxy, but intact. The stars of both galaxies would survive the merger. The planets orbiting those stars would survive. The raw material of 2 galaxy-scale systems, 2 trillion stars, and everything that orbits them would all still be present on the far side of the event. What would be destroyed is something more abstract, and in some ways more poignant, the independent existence of both galaxies as distinct structures. The Milky Way, as a separate, organized, identifiable spiral galaxy, would cease to be. Andromeda, as a separate, organized, identifiable spiral galaxy, would cease to be. What they were, the particular arrangement of their stars, the character of their arms, the specific geometry of their disks, the identities we have given them as individual objects, all of that would be subsumed into something new that is neither of them and both of them simultaneously. It is, in every meaningful sense, a transformation rather than a destruction, a reorganization of the same material into a different configuration. The atoms in every star in the Milky Way will still be present in Milkomeda. The mass is conserved. The angular momentum of the system, integrated across all the complex new orbits, is conserved. The information, in some sense, is conserved, though distributed through a system so thoroughly scrambled that recovering the original structure would be effectively impossible, like trying to reconstruct a sandcastle after the tide has come in and receded. The sand is all still there, the castle is not. There is a philosophical resonance to this outcome that science does not usually dwell on, but which seems worth acknowledging here. The Milky Way galaxy has been the home of everything we have ever known. Every human being who has ever lived, every civilization that has ever built anything, every organism that has ever drawn breath on this planet, all of it has existed within the gravitational structure of this particular spiral galaxy, embedded in one specific arm, orbiting one specific center. The Milky Way is not just a setting, it is, in the deepest possible sense, the home we did not choose and cannot leave. And if the collision happens, it will be gone. Not consumed by something alien, but merged into something that contains it, digested into a larger identity that has no particular memory of what its components were. Andromeda, coming toward us at 110 kilometers per second, is not a destroyer. It is, if you want to think about it this way, a collaborator in a transformation neither galaxy planned and neither galaxy can avoid. The outcome, Milkomeda, is not better or worse than either parent. It is simply different, quieter, smoother, redder, older. A galaxy that has been through something enormous and come out the other side into a long, patient, slowly darkening future. But this entire vision, the elliptical shape, the aging stellar population, the gradual quenching of star formation, the long, slow dimming toward a universe of red dwarfs and darkness, assumes one thing that we have been treating as given throughout this entire journey. One thing that we established as the premise of the entire collision narrative, and which we have been building on through every section of this story. One thing that the scientific consensus held as settled for more than a decade, that textbooks taught without qualification, that documentaries visualized with confident timelines and dramatic music. It assumes the collision happens. And as of June 2025, that assumption is no longer something we can make without pausing, because the most carefully constructed, most confidently stated prediction in popular astronomy, the one thing about the deep future that scientists were prepared to say with genuine certainty, was quietly revised from near inevitability to something that looks, in the honest light of a new paper and 100,000 simulations, a great deal more like a coin flip. The settled future of 2 trillion stars turns out to be anything but settled, and understanding why requires going back to the beginning of how we measured this system and recognizing the one thing we forgot to account for. Part 10. The measurement that broke the future. In June of 2025, a paper appeared in Nature Astronomy that went largely unnoticed outside the astrophysics community. Its title was Technical. Its subject was the probabilistic modeling of the future trajectory of the Andromeda Galaxy relative to the Milky Way. Its lead author was Til Sawala, and its central finding, if taken seriously, does something remarkable. It dismantles the confident collision narrative that textbooks had been telling for over a decade, not by finding new data about Andromeda, not by discovering some previously unknown object in its path, but by correcting something about our understanding of ourselves. That distinction matters enormously, and we are going to come back to it. But first, we need to build the conceptual foundation for what Sawala and colleagues actually did, because the core of their argument rests on a concept that sounds almost trivially simple and turns out to be anything but. The concept is called a reference frame. When you measure the velocity of anything, a car, a baseball, a galaxy, you always measure it relative to something else. This is not a limitation of our instruments or a gap in our knowledge. It is a fundamental feature of physics, built into the structure of the universe at the deepest level. There is no absolute velocity. There is no fixed backdrop against which all motion can be measured. There is only relative velocity, how fast this thing is moving compared to that thing from this particular perspective. When you say a car is traveling at 100 kilometers per hour, you mean relative to the road. When you say a plane is moving at 900 kilometers per hour, you mean relative to the ground below it. The plane is simultaneously moving at a very different velocity relative to the jet stream, or relative to the surface of the sun, or relative to the center of the Milky Way. All of those statements are equally valid, and they all give different numbers. When astronomers say that Andromeda is approaching at 110 kilometers per second, they mean relative to something, and for decades, that something has been the Milky Way. The Milky Way is where we are. It is the natural 0 point for any measurement we make of the local universe. We are inside it, we observe from within it, and so we naturally express the motion of everything else relative to it. This is sensible. It is convenient. It is, in almost every practical context, perfectly reasonable. But it contains a hidden assumption that almost nobody thought to question, because it was so deeply embedded in the framing of the problem that it was effectively invisible. The assumption is this, that the Milky Way's own position and motion within the local group can be treated as approximately stationary for the purposes of calculating the Andromeda collision, that the Milky Way is a stable, fixed reference point. That, when we use it as the 0 of our velocity measurements, we are not inadvertently smuggling in an error. That assumption, it turns out, is wrong. And the thing that makes it wrong is an object that has been sitting in plain sight for centuries. The Large Magellanic Cloud is a satellite galaxy of the Milky Way. From the southern hemisphere, it is visible to the naked eye on any clear night, a detached, luminous patch of sky that looks like a piece of the Milky Way that somehow broke free and drifted slightly away. It is familiar enough to southern hemisphere observers that it barely registers as remarkable. It was known to navigators for centuries before anyone understood what it actually was. And for a long time in modern astronomy, it was modeled as a relatively minor object, a small satellite galaxy containing perhaps 10 billion solar masses, orbiting at a distance of around 160,000 light-years. At that size, it would exert a modest gravitational pull on the Milky Way, enough to note, but not enough to significantly affect any large-scale dynamical calculation. More recent measurements have changed that picture substantially. Revised estimates of the Large Magellanic Cloud's mass have pushed the number dramatically higher, potentially up to 250 billion solar masses. To put that in context, the Milky Way itself is estimated to contain roughly 1 trillion solar masses of total mass, including its dark matter halo. That means the Large Magellanic Cloud, on the revised estimates, contains something in the range of a quarter of the Milky Way's total mass. That is not a minor satellite. That is a major gravitational player, and it is not sitting still. It is orbiting the Milky Way, moving through the local group, and in doing so, it is exerting a continuous gravitational tug on the Milky Way itself. Here is the critical detail. That tug is not aligned with the direction from the Milky Way to Andromeda. The Large Magellanic Cloud is pulling the Milky Way sideways in a direction that has a significant component perpendicular to the line connecting the Milky Way and Andromeda. And that perpendicular component, even if it is small in absolute terms, matters enormously when you propagate it forward through billions of years of gravitational dynamics. To understand why, think about the concept of the barycenter, the center of mass of a gravitational system. When multiple massive objects are interacting gravitationally, the most natural and physically meaningful way to describe their trajectories is not relative to any single object, but relative to the system's overall center of mass. The Earth and Moon do not orbit each other in the way we naively picture it, the Earth sitting still while the Moon circles around it. Both bodies actually orbit their shared center of mass, which happens to be located inside the Earth, because the Earth is so much more massive, but is not at the Earth's center. From outside the system, what you see is both objects tracing paths around a common point. The same principle applies to the local group. The Milky Way, Andromeda, and all their satellites are moving through the local group relative to a common center of mass. The correct way to analyze the Milky Way-Andromeda trajectory is to describe both galaxies' motions relative to that barycenter, not relative to the Milky Way itself. And when you do that, when you properly account for the fact that the Large Magellanic Cloud is tugging the Milky Way away from the barycenter in a direction that does not point at Andromeda, the Milky Way's effective trajectory through the local group looks meaningfully different from what the simpler models assumed. An analogy helps here, and it is one of those analogies that actually does the work rather than just decorating the explanation. Imagine two people walking toward each other across a large room. You are trying to predict whether they will collide. You carefully measure one person's walking speed and direction, and you extrapolate their path forward. But the second person, the one you are treating as your reference point, is being nudged sideways by someone standing just behind them, pushing gently but persistently in a direction perpendicular to their forward motion. If you do not account for that nudge, your prediction of whether the two people collide is going to be wrong, not because you measured the first person incorrectly, but because you did not fully characterize the motion of the reference point itself. A small sideways nudge, accumulated over enough steps, is enough to move someone from a path that leads to collision to a path that leads to a near miss. That is precisely the situation with the Milky Way and the Large Magellanic Cloud. The Large Magellanic Cloud is the person standing behind the Milky Way, providing the nudge. The nudge is not enormous in any given moment, but over billions of years, even a small additional velocity component compounds. Small errors in initial conditions, when propagated forward through the nonlinear gravitational dynamics of a multi-body system, do not stay small, they grow, and when they grow enough, they change qualitative outcomes, not just the precise timing of a collision, but whether a collision happens at all. This is where the Sawala paper's methodology becomes important. because Sawala and colleagues did not simply recalculate the collision with updated numbers and report a new answer. They approached the problem statistically, in a way that honestly reflects the genuine uncertainties in the system, rather than pretending those uncertainties do not exist. The technique they used is called a Monte Carlo simulation, and the name comes from the famous casino in Monaco, a reference to the role of randomness in the method. The basic idea is this: instead of running a single simulation with your best guess values for every parameter, you run an enormous number of simulations, each time drawing the parameters from the full range of values that are consistent with the observational data. You let the computer roll the cosmic dice, effectively 100,000 times. Each simulation starts from slightly different initial conditions, slightly different mass for the Large Magellanic Cloud, slightly different velocity for Andromeda, slightly different mass for the Milky Way's dark matter halo, all varying within the error bars of current measurements. Then you run each simulation forward through billions of years and record the outcome: collision, flyby, or permanent separation. When you look at the distribution of outcomes across all 100,000 simulations, you get something much more honest than a single predicted future. You get a probability distribution, a map of how likely different futures are, given everything we currently know and the full range of what we currently do not know. Some of those simulations produce a direct collision in roughly 4 billion years, consistent with the classic model. Others produce a flyby. Others produce a merger that happens much later, on timescales of 8, 10, or more billion years. And a meaningful fraction produce permanent separation, a future in which the Milky Way and Andromeda never merge at all. The numbers that emerge from this analysis are stark in their departure from the previous consensus. In the classic model, where the Large Magellanic Cloud's influence was either underestimated or simply left out of the calculation, the probability of a direct collision within 5 billion years was treated as extremely high. Some analyses put it at 90% or better. In the Sawala simulations that properly incorporate the Large Magellanic Cloud and propagate its influence forward through the full uncertainty range, that number drops to approximately 2% within 5 billion years. If you extend the window to 10 billion years, the probability of some kind of merger rises to roughly 50%, but a 50% probability is a coin flip, not a certainty. The most confidently stated prediction in popular astronomy has become, in the language of honest statistics, genuinely uncertain. And here is the thing that deserves to be said slowly and clearly, because it is the most important sentence in this entire section. Nothing about Andromeda changed. The smudge is still there. It is still 2.5 million light-years away. It is still approaching at 110 kilometers per second. Every measurement Vesto Slipher made in 1912, every measurement the Hubble Space Telescope made in 2012, every carefully calibrated number that went into the collision models over the past century, all of it is still valid. Not a single observation of Andromeda was revised. Not a single number describing Andromeda's mass, velocity, or trajectory was updated by the 2025 paper. What changed is our understanding of ourselves, of the Milky Way's own motion, of the platform we have been standing on while we made all those careful measurements of the incoming train. We discovered that our platform is not stationary. We discovered that it is drifting sideways under the gravitational influence of an object we had been underestimating for decades, and that the drift is large enough, over long enough timescales, to change the outcome from collision to something far less certain. This is an epistemological gut punch of the first order, and its implications extend well beyond the specific question of whether Andromeda and the Milky Way will merge. It raises a question that should make any scientist or science communicator pause. What else are we getting wrong by assuming we are stationary? What other predictions rest on the implicit assumption that our local reference frame is stable and well characterized? What other objects in the local group have poorly constrained masses that we have been ignoring because they seemed too small to matter, and that will turn out to matter in ways we have not yet calculated. The Andromeda collision was supposed to be the easy case, the one prediction about the deep future where we had enough information to be genuinely confident. If the easy case turned out to be this uncertain, what does that tell us about every harder case we have not yet examined with the same scrutiny? That question does not have a comfortable answer, but it is exactly the right question to be asking. Part 11. 3 futures instead of one. Where once there was a single predicted future for the Milky Way and Andromeda collision, starburst, merger, Milkomeda, there are now, in the light of the 2025 paper, at least 3 genuinely distinct possible futures, each with its own character, its own timeline, and its own emotional weight. They are not variations on a theme. They are fundamentally different stories, leading to fundamentally different endings for 2 trillion stars and every planet that orbits any of them. And all 3 of them are consistent with everything we currently observe. The first scenario is the one we have spent most of this story describing in detail, and it deserves to be named clearly for what it now is, the classic model demoted. This is the direct collision, the future that textbooks taught, that documentaries visualized, that science communicators described with the quiet confidence of settled fact for more than a decade. In this scenario, the sideways velocity of the Milky Way relative to Andromeda is small enough that the 2 galaxies approach each other nearly head-on. Andromeda grows in the sky over billions of years, from a smudge to a structured disk to a dominant presence that eventually spans a significant fraction of the visible heavens. The tidal forces begin distorting both galaxies before they even touch. The first close passage triggers the starburst. The black holes at the centers of both galaxies sink toward each other through dynamical friction, form a binary, and ultimately spiral together in a burst of gravitational waves. Milkomeda emerges from the chaos, a new elliptical galaxy, smooth and featureless, containing everything both parent galaxies were, reorganized into something neither of them resembles. This future remains real. The physics that describes it is correct. The simulations that detail it are valid. Nothing about the 2025 paper makes this scenario impossible or even implausible. What the paper does is assign it an honest probability, roughly 2% within 5 billion years, rising to roughly 50% if you extend the window to 10 billion. The classic collision is no longer the expected outcome. It is one outcome among several, distinguished from the others not by any new evidence against it, but by the simple fact that we finally did the math properly and discovered how wide the range of possibilities actually is. The textbook future is still on the table. It has just been moved from the category of near certainty to the category of genuine possibility, which turns out to be a very different place to live. The second scenario is in many ways the most dynamically interesting of the 3, and it is a possibility that older models largely set aside without giving it the attention it deserves. This is the flyby, a future in which the Milky Way has accumulated enough lateral velocity pushed by the gravitational nudge of the Large Magellanic Cloud to avoid a direct collision on the first approach, but not enough to escape Andromeda's gravitational influence entirely. The 2 galaxies come close. They interact deeply, and then they pass each other, continue on their separate trajectories, and for a while at least move apart again. The flyby scenario is worth visualizing carefully because the experience of it from the inside would be extraordinary in ways that are different from, but not necessarily less dramatic than, the full collision. Andromeda would still approach. Over billions of years, the smudge in the sky would still grow into a structured disk, still develop into one of the most visually dominant objects in the night sky. The tidal forces would still operate. They begin acting on both galaxies long before any stars from one galaxy enter the space of the other, and a close flyby would generate tidal tails from both systems, long streamers of displaced stars arcing outward from both galaxies in great curves, Some stars from the Milky Way would end up on trajectories that carry them toward Andromeda's sphere of influence, and vice versa. The two galaxies would exchange stellar material the way two passing ships might exchange wake turbulence, not intentionally, not completely, but genuinely and permanently. Star formation would be elevated in both systems during the close approach, as the gravitational interaction compresses gas clouds and triggers new bursts of stellar birth. Not at the full intensity of a direct merger starburst, the compression would be less severe, the interaction less thorough but measurably elevated, enough to light both galaxies up across multiple wavelengths for hundreds of millions of years. And then slowly, over timescales that would dwarf the entire duration of the approach, Andromeda would begin to recede. The apparent size that had been growing for billions of years would reach a maximum and then start, almost imperceptibly at first, to shrink. The galaxy that had dominated the sky would fade back toward a smaller angular size. The tidal tails would persist for billions of years, visible reminders of the encounter, but both galaxies would gradually restabilize into recognizable structures distorted, ragged at the edges, trailing stellar streams, but still broadly intact as separate systems. This is where the flyby scenario gets genuinely complicated, because the story does not necessarily end there. Two galaxies that pass close enough to exchange stars and generate tidal tails have also exchanged gravitational energy. The interaction slows both of them down relative to the local group's center of mass, a process called dynamical friction, operating at the scale of entire galaxies rather than individual stars. A system that has lost kinetic energy to a gravitational interaction may find itself on a different trajectory than the one it was on before the encounter, and a different trajectory, propagated forward through billions of years of gravitational dynamics, might bring the two galaxies back toward each other for a second encounter and a third. So the flyby scenario is not necessarily a scenario in which the merger never happens. It may be a scenario in which the merger is simply delayed, stretched out over a far longer timescale, preceded by one or more close approaches that each distort both galaxies further before the final interpenetration eventually occurs. The merger that was supposed to begin in roughly 4 billion years might instead begin in 10 billion, or 15, or longer. The starburst that was supposed to ignite during the first passage might ignite instead during a second or third pass in a galaxy that by then looks nothing like the Milky Way we inhabit today. Whether a delayed merger actually occurs depends on the precise energetics of the flyby, how much kinetic energy the two galaxies lose to the interaction, whether the residual bound orbit is tight enough to guarantee eventual return, and crucially, what the expanding universe is doing on those timescales. Which brings us to a dimension of this problem that does not receive enough attention in most discussions of the Andromeda collision: dark energy. The universe is expanding, and that expansion is accelerating. The acceleration is driven by dark energy, the mysterious component of the cosmos that acts, in effect, like a repulsive pressure built into the fabric of space itself, pushing distant structures apart faster and faster as time goes on. On the scales we navigate in daily life, and on the scales of our solar system, and even on the scales of the galaxy, dark energy is utterly negligible. Its effect only becomes meaningful at the distances between galaxy clusters and beyond. But on timescales of tens of billions of years, even modest effects accumulate into something significant. The Milky Way and Andromeda are, under current models, gravitationally bound to each other. They form part of a local structure, the local group, whose internal gravity is sufficient to keep it from being torn apart by the background expansion of the universe. But the boundary between bound and unbound is not infinitely sharp, and dark energy shifts that boundary over time by adding a steadily growing component of separation velocity to every pair of objects, regardless of their local gravitational relationship. In scenarios where the Milky Way and Andromeda are only weakly bound, barely enough energy deficit to guarantee eventual return after a flyby. The growing influence of dark energy over tens of billions of years could tip the tender balance. A pair of galaxies that would, in the absence of dark energy, eventually return to each other after a first flyby, might instead find that the accelerating expansion slowly stretches the gap between them beyond the point of gravitational return. The merger that was only delayed might become the merger that never happens, courtesy of a force operating on scales and timescales that make the Andromeda collision itself look like a local, short-term event. The third scenario is the one that departs most completely from everything the classic model assumed. It is permanent separation, a future in which the Milky Way's lateral velocity, accumulated through the continuous gravitational nudge of the Large Magellanic Cloud, is large enough not only to prevent a direct collision, but to place the Milky Way on a trajectory that is genuinely unbound relative to Andromeda, not delayed, not interrupted. Unbound in the technical physical sense, the total energy of the Milky Way Andromeda system, properly calculated, is positive rather than negative, meaning the kinetic energy of their relative motion exceeds the gravitational potential energy holding them together. In physics, an unbound two-body system has exactly one long-term outcome: separation. Permanent, final, irrevocable separation. If the Milky Way and Andromeda are on an unbound trajectory, then no matter how long you wait, 5 billion years, 10 billion, 100 billion, they will not return to each other. They will continue moving apart, each carrying their stellar populations into their own independent futures, the gap between them growing wider with every passing era until the cosmological expansion renders them invisible to each other across a universe that has grown too large and too dark for light to bridge the distance. What would the Milky Way's independent future look like in this scenario? It would continue to evolve, as it has for the past 13 billion years, largely on its own terms. The Large Magellanic Cloud, having provided the nudge that changed everything, would eventually complete its current orbital interaction with the Milky Way, possibly merging with it on a timescale of a few billion years. A minor merger compared to what the Andromeda collision would have been, but not without consequences. The small Magellanic Cloud, the other nearby satellite galaxy, would follow its own fate. Dwarf galaxies in the local group that are gravitationally bound to the Milky Way would continue to be absorbed over billions of years, as they have been throughout our galaxy's history. The Milky Way would grow incrementally, feeding on its small satellites, without ever experiencing the catastrophic transformation that a full Andromeda merger would have produced. The spiral arms would persist, the disk would remain intact. The orderly rotation of hundreds of billions of stars around the galactic center would continue for tens of billions of years, gradually losing its most massive and luminous members to stellar evolution and supernova, slowly shifting its stellar population toward the long-lived red end of the mass spectrum. The Milky Way would age, but it would age as itself recognizably the same structure, just older, quieter, gradually dimming toward the same long future of red dwarfs and darkness that Milkomeda would face after a merger, just getting there by a different road. And Andromeda, in this scenario, would follow its own independent path through the local group, still a trillion stars. Still a spiral galaxy, probably, unless its own satellite interactions eventually disturb its disk. Still moving through a local group that is growing darker and more isolated as cosmic expansion carries the rest of the universe away. Two great galaxies that came close enough to distort each other, close enough to exchange stars and generate tidal tails, and briefly dominate each other's skies, and then parted forever, each carrying the gravitational memory of the encounter in the form of stellar streams and disturbed outskirts, but neither ever completing the merger that a century of astronomy described as inevitable. Three futures, one that ends in Milkomeda, one that ends there eventually, after a more complex journey, one that ends with two separate galaxies aging independently in a universe that neither of them will ever fully see again. All of them physically real. All of them consistent with current observations. All of them, in their different ways, containing everything that the Milky Way and Andromeda currently are: 2 trillion stars, billions of planetary systems, whatever forms of complexity exist within them, just arranged differently, following different trajectories, heading toward different versions of the long, dark future that awaits everything in the universe. The question of which future is actually ours is one that current science cannot definitively answer. And sitting with that uncertainty, really sitting with it rather than resolving it prematurely into false confidence in either direction, might be the most honest thing we can do with everything this story has given us. Part 12. The deeper problem. Here is the thing that has been quietly sitting underneath this entire story, waiting to be named. It is not about Andromeda. It is not about the Large Magellanic Cloud, or the barycenter of the local group, or the specific numbers in the Sawala paper. It is about something deeper than any of those things, something about the relationship between knowledge and confidence, between detail and certainty, between the stories science tells about the future and the foundations those stories actually rest on. The Andromeda collision was supposed to be the easy case. Let that sit for a moment, because it is important. Cosmology is a field that lives with uncertainty in a way that most sciences do not. The nature of dark matter, what it actually is, what particle or field or exotic phenomenon constitutes the invisible mass that holds galaxies together, remains genuinely unknown after decades of extraordinarily sophisticated searching. The source of dark energy, the force or property of space-time that is causing the expansion of the universe to accelerate, is, if anything, even more mysterious. A placeholder name for something we can measure in its effects, but cannot explain in its origins. The conditions during the first milliseconds after the Big Bang, the question of whether the universe is finite or infinite, the ultimate fate of everything at heat death, or big rip, or big bounce, or whatever terminal state the cosmos is heading toward, all of these are open questions, and nobody is particularly surprised that they are open. They are hard problems. They involve physics at energies we cannot replicate, distances we cannot observe, timescales we cannot model without enormous uncertainty. Of course, they are unsolved. Of course, they are contested. That is what hard problems look like. But the Andromeda collision was supposed to be different. It was supposed to be the case where we had crossed over from speculation into genuine knowledge. A system containing 2 well-studied galaxies at a well-measured distance, approaching each other at a well-measured speed, governed by the same gravitational physics that has been tested to extraordinary precision in every other context we have applied it to. It was, in the language of physics, a well-characterized system. We knew the masses, we knew the velocities, we knew the distances, we had run the simulations, we had cross-checked the results. We had a timeline, we had a name for the result. For over a decade, it was presented to the public as exactly that, a known future, a solved problem, one of the rare moments when astronomy could point to a specific event billions of years from now and say, with genuine confidence, that it would happen. The 2025 paper does not just revise that specific prediction. What it does, what its deeper significance actually is, once you look past the specific numbers, is reveal something more general about the limits of prediction in complex gravitational systems. Something that weather forecasters have understood for decades. Something that chaos theorists formalized in the latter half of the 20th century. Something that had, apparently, not been fully internalized in the context of galaxy dynamics, at least not with sufficient force to prevent a decade of overconfident communication about the future of the Milky Way. The concept is called sensitive dependence on initial conditions. Most people know it through the butterfly effect metaphor, the idea that a butterfly flapping its wings in Brazil can, through a chain of atmospheric interactions, influence whether a tornado forms in Texas. The metaphor is whimsical, but the underlying mathematics is serious and well established. In any dynamical system governed by nonlinear equations, small differences in starting conditions do not stay small. They grow. Under the right conditions, they grow exponentially. A difference of 1 part in a million in the initial velocity of a particle might produce no meaningful divergence in its trajectory for a long time, but eventually, at a timescale determined by the system's specific dynamics, that tiny initial difference will have amplified into a qualitatively different outcome, not a slightly different path, a completely different destination. Gravitational systems involving multiple interacting bodies are among the most thoroughly nonlinear dynamical systems that exist. The three-body problem, the question of predicting the long-term behavior of three massive objects interacting gravitationally, has no general closed-form solution. It was one of the great mathematical disappointments of the late 19th century, when Henri Poincaré demonstrated that the equations describing three gravitationally interacting bodies could not, in general, be solved analytically. You can simulate them numerically, stepping forward through time in small increments, but the accumulation of small errors in numerical integration, combined with the exponential sensitivity of the system to initial conditions, means that long-term predictions become increasingly unreliable as you push further into the future. The Milky Way Andromeda system is not a three-body problem. It is an n-body problem involving two major galaxies, dozens of satellite galaxies, and the dark matter halos that surround all of them. It is, in the formal mathematical sense, an extraordinarily non-linear system being evolved forward through 5 billion years of chaotic dynamics. This is not a story of bad science. That needs to be said clearly and more than once, because the easiest misreading of everything we have covered in this section is to conclude that the astronomers who calculated the collision timeline were sloppy or overconfident or insufficiently rigorous. They were none of those things. The 2012 Hubble measurement of Andromeda's tangential velocity was a genuine technical achievement, tracking the positions of individual stars in a galaxy 2.5 million light-years away against the background of even more distant reference objects, extracting a sideways velocity from the data with unprecedented precision. The simulations of the collision dynamics built on that measurement were valid physics executed with care. The models were the best that could be constructed with the data available at the time, and they produced results that were internally consistent and genuinely informative. The error, and it is an error, even if an understandable one, was in the communication of uncertainty. The most likely outcome in the models of that period happened to be very likely, something on the order of 90% probability of direct collision within 5 billion years, according to some analyses. And when the most likely outcome is that likely, there is a powerful temptation to stop describing it as probabilistic and start describing it as certain. To round 90% up to done deal. To present the simulation results not as one set of possible futures weighted by probability, but as the future, the actual, specific, forthcoming reality. The textbooks did this, the documentaries did this, the popular science articles did this, and it seemed justified because the numbers supported it. The problem was not that the numbers were wrong. The problem was that the model generating those numbers was missing something important, and when the missing piece was added, the probability distribution shifted dramatically. The specific missing piece was the Large Magellanic Cloud. But the broader and more uncomfortable lesson is, what else might be missing? What other object in the local group has a poorly constrained mass or an inadequately measured velocity that matters to some calculation we currently treat as settled? The dark matter halos of the Milky Way and Andromeda are defined by inference rather than direct observation. We deduce their extent and mass from the rotational velocities of stars and gas, from gravitational lensing measurements, from the dynamics of satellite galaxies, Those inferences carry real uncertainty. The halos could be more massive than current models suggest, or less. Their exact shapes, their precise extents, the degree to which they overlap already at the current separation, all of these matter to the dynamics of the approach, and none of them are known with the kind of precision that eliminates their contribution to the overall uncertainty budget. There are also dozens of smaller satellite galaxies orbiting both the Milky Way and Andromeda dwarf galaxies, ultra-faint galaxies, stellar streams that represent the disrupted remnants of galaxies that have already been partially absorbed. Many of these were discovered only in the last decade, as survey technology improved enough to detect objects of extremely low surface brightness. Their total mass contribution to the local group's dynamics is only beginning to be properly characterized. Any one of them, if it turns out to be more massive than currently estimated, could shift the barycenter of the local group, alter the effective velocity of its parent galaxy, and nudge the Milky Way Andromeda trajectory in ways that the current generation of models does not capture. This is the epistemological lesson that the Andromeda revision forces us to sit with. We are always modeling systems with incomplete information. There is no alternative to this, because the information available to us is always finite and always imperfect. Every model we build is a simplification of a reality that is more complex than any model can fully capture. Every prediction we make rests on assumptions about which factors matter enough to include and which can safely be ignored. Those assumptions are not arbitrary. They are informed by physics, by observation, by the best judgment of expert practitioners. But they are assumptions, and the history of science is full of cases where an assumption that seemed safely ignorable turned out to be load-bearing. When the assumption that is load-bearing turns out to be wrong, when the object we decided to ignore carries a quarter of the mass of the Milky Way, the predictions built on that assumption do not just become slightly less accurate. They change qualitatively. The outcome shifts from near certain to genuinely uncertain. The confidence that had accumulated over a decade of consistent modeling turns out to have been confidence in a model rather than confidence in the future. And those are very different things. There is a philosophical point here that goes deeper than the specific case of the Andromeda collision, and it has to do with the relationship between detail and certainty, a relationship that turns out to be far less straightforward than intuition suggests. We tend to assume that more detailed knowledge means more confident prediction, that a highly specific, richly elaborated model of a future event is a more reliable model, that the more work you have done on something, the more you can trust your conclusions about it. This assumption is not unreasonable in many contexts it holds. But the Andromeda case is a clear counterexample. We know more about what the Milky Way Andromeda collision would look like than we know about almost any other event in the deep future of the cosmos. We have simulated the starburst phase with models that track individual molecular cloud interactions. We have modeled the tidal tail geometry with resolution sufficient to trace individual stellar streams. We have followed the dynamical friction spiral of the supermassive black holes from galaxy-scale separations down to parsecant-scale binaries. We have run statistical analyses of the solar system's fate displacement probabilities, ejection probabilities, capture probabilities across thousands of realizations of the merger. The level of detail is genuinely extraordinary, and none of that detail tells us whether the event is actually going to happen. You can know precisely what would occur inside a scenario without knowing whether that scenario will occur. The map of a territory you may never visit is still a valid map. The physics of the collision is correct regardless of whether the collision takes place. But the detail of the physics had been, for a decade, substituting for certainty about the premise. The rich elaboration of what the collision would look like had been quietly lending the impression that the collision was a known future, rather than a well-understood contingency. Detail and certainty are different things. Confusing them is one of the most subtle and pervasive errors in how we communicate science to the public, and the Andromeda case is perhaps the clearest illustration of that confusion ever produced. Come back, now, to the smudge in the sky, 2.5 million light-years away, 1 trillion stars, moving toward you at 110 kilometers per second. The light reaching your eyes from Andromeda tonight left its source before anatomically modern humans walked on this planet, before our species existed, before our ancestors had developed the cognitive architecture that would eventually allow them to build telescopes and spectrographs and space observatories, before any human thought had ever been thought. That light has been traveling through the void for longer than our entire evolutionary history, and it ends its journey on your retina in this moment, carrying information about 1 trillion stars that are still out there, still moving, still following the trajectories that the universe set for them at the beginning of everything. That smudge contains, within it, the potential for one of the most spectacular gravitational events in the history of the local group, tidal tails, stretching across hundreds of thousands of light-years. A starburst producing hundreds of millions of new stars in a cosmological eye blink. Supernova waves sweeping through a combined system of 2 trillion stars, seeding the interstellar medium with heavy elements forged in stellar cores. The energetic awakening of 2 supermassive black holes, as infalling gas ignites their accretion disks into quasar-level luminosity. The final in-spiral of those black holes into a gravitational wave burst that briefly carries more energy than every star in the observable universe radiates in the same moment, expressed entirely in ripples of space-time that no eye and no conventional instrument could ever detect. Or the smudge contains none of that. Or it contains a partial version, a flyby, a glancing interaction, a distortion of both galaxies that leaves the headlines intact but the catastrophe unfinished. We cannot tell which of those futures is real by looking at it. The smudge looks identical in all 3 scenarios. It will continue to look identical for billions of years, right up to the moment the trajectories of these 2 gravitational systems diverge past the point of no return. And that moment is 3 to 4 billion years away, a span of time so far beyond the reach of human experience that every civilization that has ever existed, every empire that has ever risen and fallen, every generation that has ever looked up at this same smudge in the same sky, is compressed by that timescale into something smaller than a rounding error. We are standing at the beginning of a story whose ending the universe itself has not yet determined, or if it has determined it, has not told us. The physics is correct. The mathematics is valid. The simulations are as beautiful and as carefully constructed as anything in modern astrophysics. And the question that sits at the center of all of it, whether the night actually comes, whether the sky actually breaks open, whether Andromeda and the Milky Way actually find each other after a journey of billions of years across 2.5 million light-years of void, that question remains open. Perhaps that is the most honest thing this story has to offer. Not the spectacle of the collision, though the spectacle is real and extraordinary. Not the revised probability, though the revision matters and deserves to be understood. But this, that the closer you look at any confident prediction, the more clearly you can see the assumptions holding it up. That the most important discoveries in science are sometimes not the things you find, but the things you realize you do not know. That the most dangerous kind of certainty is the kind that does not know what it is missing, the kind that has done all the work, checked all the calculations, run all the simulations, and arrived at a confident answer without noticing the one variable it forgot to include. Somewhere in the local group right now, there is a gravitational conversation happening between the Milky Way and the Large Magellanic Cloud and Andromeda, 3 major gravitational systems and their dozens of satellites, their invisible dark matter halos, their billions of years of accumulated momentum, all following trajectories set by initial conditions at the beginning of the universe, obeying equations we understand with precision and applying them to a future we cannot quite pin down. Go outside tonight if you can. Find the constellation Andromeda. Find the smudge, the faint, elongated blur of light sitting just off the main line of stars, containing 1 trillion suns, 2.5 million light-years away. Look at it for a moment before you look away. It is not just a galaxy, it is a question mark. A 2.5 million light-year wide question mark made of 1 trillion stars traveling at 110 kilometers per second, asking us, in the gentlest possible way, whether we have been measuring the future from the right place, and whether we would even know if we had not been.